online talk, but let's see. I'll try my best. So today we are going to look into um, yeah. Today we are going to look into this decoherence and today we'll look into decoherence and Krauss operators, noise in general. What I have planned, and let's see how much time allows us to do, is to go through the theory of these things a bit. And also at the same time, if at least we can get 30 minutes of something, I can show you how you can do all the things that we discussed today on Qiskit. It's very simple to do all of those. Um, just one question mainly to the attendees. I got to know that one of the previous speakers have already covered block spheres. So I guess all of you are at least comfortable with what is a block sphere, why it is needed, and this kind of thing, right? Just see if any of you want to on a chat, just uh, say if you are okay with block spheres, then I won't go too much into the details of what is block sphere. But anyway, I'll do a small overview. Uh, yeah, I need to do that. Okay, please. Someone is saying, please explain in detail. Okay, let's go into this. Let me share my screen and. So I hope my screen is visible, and let us get into this. And we need to start with what is block sphere. So let's go into that. We know, all of us, we know that whenever we have a quantum state, we usually um, take it as a state vector. Say we have a quantum state, we write it as psi. So it is a state vector, and it's a vector in Hilbert space. Sorry, it's a vector in Hilbert space. And we have already seen what are the different stuffs that we can do. Any operation on this is a unitary operator. So this psi will evolve as some phi will be some u times psi, where u is a unitary. And we have seen all of these that we can measure it in a basis, and the probability of obtaining an outcome, say small b, is given by this. This is the Born rule. So we know all of this. Um, Now the question is that this state vector representation has some limitations. And when we think of this limitation, the first thing that comes into mind is entanglement. So entanglement, we know, say this state, say 1 over root 2, 0, 0 plus 1, 1. This state we know is entangled. So what it means is that I have a very nice way, a very nice mathematical representation of this 2-qubit state, say call it psi 1, 2, this 2-qubit state. But if I ask you that what is psi 1, so like what is the first qubit, say call it psi 1, what is that? What is the second qubit? Give me a representation of what the first qubit is, what the second qubit is. That's where things get a bit difficult, because there is no mathematical representation of this. Um, but what I want to emphasize for once is the requirement for some other representation beyond this state vector representation psi. This actually comes even before we think of entanglement. So, um, so this is of course a limitation, that I am unable to write down what are the individual qubits. We know the individual qubits exist. I am able to give you a very nice representation of the 2-qubit state, but I cannot really give you a mathematical representation of the single qubit state. However, even before this, we come across some limitation, even before we think of entanglement or anything. So let's look into a very simple scenario where I have a say a state preparation system. This is a state preparation system. And in the state preparation system, I have a biased coin. I have a biased coin. I flip the coin. If the coin turns out to be head with probability 1 minus p, I prepare the state 0. If it turns out to be tails with probability p, I prepare the state 1. So this is my scenario here. I have a state preparation system. There is a biased coin. I toss the coin. And when I toss the coin, if it turns out to be head, which happens with probability 1 minus p, I press a button. It prepares the state 0. If it turns out to be tails with probability p, I press a different button and it prepares a state 1. Now the question here is, there is no entanglement, nothing. It's a very simple scenario. How do we mathematically represent this? If we say that, okay, so the mathematical representation of this is, say, square root of 1 minus p0 plus square root of p1. This is wrong. Why is this wrong? Because what this is telling me is this representation is a superposition. So this state that I am representing using this notation, this mathematical notation, is both in the state 0 and 1 at the same time. But what I just described here is I am either preparing the state 0 or preparing the state 1. I am not preparing both of them or some superposition of them. I am just tossing a coin here and I am preparing either 0 or 1. So this representation, if I give this kind of a mathematical representation to this problem, this is completely wrong. This representation is not correct. So the question is, how do I represent this? And the answer is we can't. Even before going into entanglement, there is even no superposition in this example that I described. Even in this example, we are unable to give a mathematical representation of the scenario. So it shows there is a limitation of this state vector notation. And what we want to do is we want to go to some other notation that is known as the density matrix notation. So what will be a density matrix? Simple. What is a state vector notation? It's a vector in the Hilbert space, right? So if my Hilbert space is H, it is a vector V that belongs to the Hilbert space. This is my psi. On the other hand, my density matrix will be an operator acting on the Hilbert space. So this will be my difference in state vector versus density matrix. Density matrix will be an operator acting on the Hilbert space. So if I think of this, say, this is my Hilbert space HA, where my psi was belonging. This is some Hilbert space HB, where the state phi belongs. And maybe there is a unitary operator U that takes me from psi to phi. So it takes me from Hilbert space A to Hilbert space B. Now, when I think of a density matrix, it no longer belongs inside this Hilbert space. It's again an operator. Call it, say, H psi. It looks kind of similar anyway. It's an operator that acts on the Hilbert space. And for this particular case, it will be represented like this. And similarly, here we will have an H phi, which will be represented like this. So there are some terminologies here. It's not very difficult. So we call this as an operator. This we know. This unitary matrix is called an operator. The moment we go to density matrix, how do I go from this density matrix to this density matrix? So previously, phi was U of psi. Now I am writing my density matrix, call it rho phi. The representation is like this. Okay, that this is a better thing. Let's use the same notation here also. Let's call these rho. That is better. So rho phi is this. We know phi is equal to u psi. So I can just say this is psi. This is the adjoint of this. So it will be psi u dagger. And then I am left with u psi u dagger. And this is simply rho psi u dagger. Right? So the evolution of my density matrix is given by this unitary U acting before versus and the unitary U dagger, the conjugate of that, the adjoint of that, acting after. So this was an operator. An operator going from here to here, it will have the form of say U dot U dagger. This dot will be the row here. This thing is called a super operator. Just there is nothing very uh, special about this term super operator. It simply differentiates between when I say operator, it acts on the state vector. When I say super operator, it acts on the density matrix. And it will be of the form U rho U dagger of that form. So there are certain requirements of the density matrix. So first, okay, so when we were thinking of state vector, first we had a representation. We saw how the representation changes. It becomes a matrix. It becomes an operator because if you take say psi, this becomes an operator. I mean, say a 4x4 matrix. This becomes a 4x4 matrix. We can take an example. Say my psi was simply A0 plus B1, then my rho psi will be psi, which will be simply A0 plus B1 times the complex conjugate A star 0 plus B star 1. So if you just break it, it will be mod of A square 0 0 plus AB star 0 1 plus B A star 1 0 plus mod of B square 1 1. So this I can represent like a matrix where this is mod of A square, this is mod of B square. This part is A B star, this part is A star B. So first is representation difference. The difference in representation previously, this was just a column vector. So if my psi was A0 plus B1, this becomes a column vector like A and B. So now we see that the difference is that it becomes a matrix. Second is we wanted to go for how the system evolves. Well, we have just seen that previously it was an operator that acts on a state vector, gives another state vector. Now we have something that we call as a super operator. It is just deriving from that operator itself, nothing very different. So we have something called a super operator, which acts on the density matrix to give another density matrix. The third thing was the measurement, right? Now, if you look into this state, what is the probability of 0? It is mod A square. What is the probability of 1? It is mod B square. And where do we see here mod A square and mod B square? Here in the diagonals. Here we have mod A square, here we have mod B square. So since this mod A square and mod B square, these are the probabilities. So we need to have the diagonal should add up to 1. So the very, very important requirement is that trace of rho is equal to 1. This is the first and foremost requirement that we have. And just mind at this point, I am not thinking of noise. We will see what happens to this think nothing will happen to the trace, but trace square when noise happens and other things. So this is the first and foremost requirement. These are mod A square, mod B square. These are my probabilities. So when I measure this, mod A square gives the probability of getting outcome 0. This gives the probability of getting outcome 1, and they add up to 1. Therefore, trace of rho should be 1. This should be preserved for any density matrix. Now the question is, what are these terms? Because when I measure a system, all I get is the classical outcomes, mod A square, mod B square. Now, the question is that, okay, so that's fine. The question is that you want to have a scenario where, because when we do measurement, eventually we have to do a measurement. And when we measure, we just get classical outcomes. So we if we think along that terms, we can say that, okay, I have a quantum system. When I measure it, the probability of getting 0 is mod A square. The probability of getting 1 is mod B square. I can even do that with a coin toss. I can have a biased coin. Don't confuse with this example. I am coming to this example soon. But just to get a scenario where you want 0, say heads with probability mod A square, tails with probability mod B square, this does not require any quantum thing. This is just a classical probability distribution. So these two terms, these two off-diagonal terms, these are the quantumness of a system, if you call it like that. So these two things, the off-diagonal terms, because the diagonal terms, they are just classical values. And when you measure, you get the diagonal terms. These off-diagonal terms are called coherence. And in some sense, this is what is the quantumness of a system. And you have already heard the name of decoherence. It was the title of this lecture, in the title of this lecture. When noise happens, what happens is when the system interacts with the environment, that's noise. When that happens, these off-diagonal terms go to 0. And if it goes to 0, this is what is called that the system is losing its coherence. That means when noise happens, we will see this. I'm just kind of jumping ahead. But when noise happens, this system turns down. This tends to something like this. And this we just discussed that this is a classical scenario where I can just do a coin toss with probability A square and B square. So this is classical. So as the system interacts with the environment, it becomes classical. And how it becomes classical is by losing this off-diagonal terms, which are called decoherence, which are called coherence. And this process of losing the coherence is called decoherence. But anyway, so this is my first requirement. Trace of rho should be equal to 1 for every scenario. There is another requirement for being a density matrix, that is, all the eigenvalues of this density matrix should be greater than or equal to 0. Because these eigenvalues, what do my eigenvalues tell me here? We know that when we measure this, the eigenvalues, so when I have a density matrix rho, and if I diagonalize this density matrix, I should be able to find a basis, say some B, where I will be able to write it down like this. So B0 plus say B1, where this Kate and Bra B1, these are the eigenstates, and just the B0 and B1, these are the eigenvalues. So when I measure this system, this system will collapse either to state B0 with probability B0, or to state this density matrix B1 with probability B1. Since these eigenvalues correspond to probabilities, these eigenvalues should be greater than or equal to 0. So this is what the second term is telling, second requirement is telling us, that rho should be greater than equal to 0. This implies that my eigenvalues should be all non-negative. And that directly translates to saying that when I measure the system collapses to one of the eigenvectors. This we already know. Even the state vector idea is this, that it will collapse to the one of the eigenvectors with the probability of the corresponding eigenvalue. So if my corresponding eigenvalue is a probability, it should be greater than or equal to 0. So that's kind of like a very quick summary of what these density matrices are about. Now let's ask the question that we started by a scenario, with a scenario where we said that, okay, I have a machine where I have a biased coin. I flip my coin. If it turns out to be head, the probability of that is 1 minus p. I press one button and it gives the state 0. Or if it is tails, I press the other button, it gives the state 1. And we argued that this superposition kind of representation is not really representing what is happening in this example. But because you will understand one thing, why so? Because when I write this kind of thing, this is not probability, this is probability amplitude. The square of this is probability. But here I am dealing with a classical mixture. This is a classical probability, a classical mixture. I am flipping a coin and accordingly I am pressing 0 or 1. There is nothing quantum in it. So for this kind of scenario, what I can do is I have a preparation system once more. This is 1 minus p. It creates the state 0. With p, it creates the state 1. I can represent this as rho 1 minus p 0 0 plus p 1 1. Just note one thing, I'm sure you have already noted, but just to point it out explicitly, when we have state vector, we are at the regime of this probability amplitude. The probability is the square of the amplitude. When we come to the density matrix, the diagonal terms are the probabilities. They are not amplitudes. They already give the probability, and you can see from here, these are the probabilities. These are not the amplitudes. This is a classical mixture of the state 0 and the state 1. The state 0 is given by probability 1 minus p. It is getting prepared with probability 1 minus p. And the state 1 is getting prepared with probability p. And in fact, you kind of really understands from this is that this in fact is an example of noise. This is a state preparation. I said that we are flipping a coin and all of those, but essentially it's kind of a noise that always we should be preparing the state 0, but sometimes we end up preparing the state 1. So this is kind of a first example of noise, but yeah, I mean, we'll look into more, not like this. Just there is one more very important thing that we need to consider. So we saw that trace of rho should be 1. What should be trace of rho square? If I want to go into that, what should be trace of rho square? So let's take example that I have a quantum state, rho is 0 0. What is rho square? Rho square is essentially 0 0 times 0 0. So it is just 0 0. Rho square is equal to rho. In fact, you can show that if you have any of these computational basis states, then rho square is always equal to rho. But what if it's a superposition state? I mean, if it is 0, you can understand. If it is 1, it will be very similar calculation, and we can understand. Say the state is plus, minus. These are all basis states. These are all eigenvectors. So we understand that for all of them, rho square will be equal to rho. That means trace of row square is equal to trace of row is equal to 1. What if my row is a superposition state? And I'll write in the density matrix notation. So just to re-emphasize, these are now probabilities. These are not probability amplitudes. I don't need to take square. These should add up to 1. So the question is, what is trace of row for this? Well, the trace of row for this is again 2/3 trace of 0, 0 plus 1/3 trace of 1, 1. What should be the trace of 0, 0? We can do a simple mathematical calculation and show that it should be 1. We can do another thing. We can do another argument. So if you write 0, 0, 0, 0 looks like this. 1, 0, 0, 0. So trace of this is basically 1. We can do another argument on top of that, even without writing down the matrix explicitly and showing what is happening. We can do a different argument, and the argument will be, what was my trace? Why was trace of row equal to 1? Because this turned out to be the probabilities, right? So naturally, this is a valid density matrix. Its trace should be 1. This is a valid density matrix. The trace should be 1. So it is 2/3 plus 1/3, which is 1. But what is the row square for this? So let's write row square first. So row square will be 2/3 0, 0 plus 1/3 1, 1 times 2/3 0, 0 plus 1/3 1, 1. So we have, say, 4 by 9, 0, 0, 0, 0 plus, let's do the 0 and 1. So it's 2 by 9, 0, 0, 1, 1 plus 2 by 9, 1, 1, 0, 0 plus 1 by 9, 1, 1, 1. So 1, 1, 1, 1. Now, naturally, this inner product is 0. This inner product is 0, which means that this term and this term anyway gets cancelled out. So we are left with this term. This inner product is 1. This inner product is 1. So that means if I do the trace of row square, it is essentially 4 over 9. Okay, let's write it down. 4 over 9, 0, 0 plus 1 over 9, 1, 1. And you can immediately see that this will become trace of 0, 0 plus 1 over 9 trace of 1, 1. So that's 4 by 9 plus 1 by 9, which is equal to 5 over 9. This is not equal to 1, and this is in fact less than 1. This is important. Not equal to 1 is not the more important thing. It's less than 1. And what you can actually show, or what you can argue from here, is just some definitions that if you have a density matrix whose trace of row square is equal to 1, this is called a pure state. If it is a pure state, you can always write a state vector representation of that. So you could have just represented this as psi. But if you have trace of row square less than 1, this is called a mixed state, and it does not have a state vector representation. Note once more, this is not a superposition state. This is in fact the type of state that we started with, that you are preparing 0 with probability 2/3 and 1 with probability 1/3. So this is in fact the type of state that we started with, the discussion that we started with. If it is a pure state, like 0 was a where did it go? Yeah, 0 was a pure state. Trace of rho square is equal to trace of rho square is equal to 1. And if you want to represent 0, you don't really need a density matrix. A state vector notification is sufficient. But if you want to represent it, if you want to represent this kind of state, this kind of state, there is no state vector representation of that. Trace of rho square is less than 1. It is called a mixed state. And this definitely requires a density matrix notation. In terms of Bloch sphere, um, I won't go into the details of how the Bloch sphere is created or anything. It will like take up a lot of time, and we will diverge from the decoherence and of Krauss operators and all of those parts. But we know that a density matrix can always be represented as a Bloch sphere, and say this is 0, this is 1, this is the equatorial plane. In the equatorial plane, you have, this is the, say this is the z-axis, the 0, 1 is the z-axis. Then the x-axis looks like this, and the x-axis has plus, plus, minus, minus. So plus is 0 plus 1 over root 2, minus is 0 minus 1 over root 2. And this z-axis, this one, this is just plus I plus I. This is the eigenstate of Y matrix. It's represented as plus and minus I. So this is what the entire Bloch sphere gives us. If it is a pure state, it belongs to the surface of the Bloch sphere. So pure state belongs to the surface of Bloch sphere. Mixed states. So if you look into this state, what is it telling us? That it is a mixture of 0 and 1. It is closer to 0, a bit farther from 1. It's 2/3 towards 0, 1/3 1. So if we look into something like this, say it is 1 minus p towards 0, and this thing downwards, this is p. So my rho actually belongs here. It is a mixed state, and it belongs inside the surface of the Bloch sphere. It is inside the Bloch sphere. It is not on the surface of the Bloch sphere. So mixed states belongs inside the Bloch sphere. And what will happen if I start increasing p? What will happen then? I'm just doing this on the z axis, 0, 1 axis, but you could have done this on any other axis. It doesn't matter. So as I start increasing p, this point will shift, shift, shift. And at this point in the origin, p and 1 minus p becomes equal. That means p becomes half, right? So this, at this point, the origin p becomes half. Then my state looks like half 0 plus half 1. What does this mean? If I measure this state, I will get an outcome 0 with probability half, outcome 1 with probability half. This is the minimum possible information that you can get from anything, right? It is just a coin toss, nothing more. This is not telling you anything. This is giving you total zero information. I mean, there is no information here. Well, it's just, it is at a 50% chance of being 0, 50% chance of being 1. It doesn't tell me anything about the system. I could have just written this without doing the calculation. I would urge you to go and do the calculation if you haven't done this before. But just from the argument that we made, I said in the beginning that I am just looking into the z-axis. I could have looked into the x-axis as well. So my rho could have been, say, 1 minus p plus 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 p minus minus. Again, if I start increasing p, I will reach this origin where the state will be 1/2 plus plus half minus minus. I could have done this from the y-axis as well. I could have taken some other axis also, not necessarily x, y. I could have just said that, okay, I like this axis. I will use this axis. I could have done that also. So any axis that I take, called is the b, again b0 plus half b1, where b0 and b1 are orthogonal. Of course, the requirement is that b0 and b1, they are orthogonal. If this condition is satisfied, it is basically the same state, the origin. So first thing is that it is not telling me it is not giving me any information. It is not also telling me whether it is like prepared via 0011. Is it coming through plus plus minus minus? Is it coming through some other basis? There are infinitely many bases that you could have selected. And all of them, when you start increasing p and take it to half, will reach the origin. And here, if you do the maths a bit, just break down this and add, you will see this state can be written as identity by P. This is called a maximally mixed state. This is called a maximally mixed state. It gives me no information. It has the maximum entropy, and you will be looking into quantum cryptography, I think, starting tomorrow or sometimes. I don't know whether they will talk about this, but if they do, great. If they don't, if you just go and look into the protocol, and if you see that when say the BB84 protocol or something, the key distribution protocols, when the communication happens, when the bit goes from Alice to Bob, if you look into the bit in the middle, within this communication, not after Bob receives and measured the state, but within the communication, it is always in this state identity by 2. So it's a maximally mixed state. It has maximum entropy. If there is a hacker who is trying to get hold of that state, all those things that you cannot copy and everything that will come into play. But it gives you zero information at in between. In fact, if you do teleportation, I mean, you can again go back and check this out. When you do teleportation, if you look into the scenario that what happens in teleportation, first, Alice is sending to Bob. So Alice will take, Alice and Bob shares an entangled state. Alice takes her part of the entangled state, her qubit, and the qubit she wants to teleport, and measures it into the Bell basis. And depending on the outcome, Alice will inform Bob, and Bob will do a unitary operator and then will measure. But we argued, I think teleportation, I don't remember, maybe I myself covered teleportation, but I didn't say it at that time for sure. if you look into this, we kind of argued that when you are doing teleportation, you need to send those two bits of classical communication. Otherwise, it will be like faster than speed and all of those. So it violates general relativity. If you mathematically look into the state, once Alice has made the measurement, but Alice has not sent any classical information to Bob yet. So what does Bob know about the system? It's a maximally mixed state. Bob knows nothing about the system. So you see how the maths so beautifully works out. One thing connects to so many different things together. But anyway, so that's kind of yeah. Let's stop talking of density matrix and block sphere up to this point. If there are any questions at this point, we can just take uh, this question. If there are any questions at this point. So there is a question on explain the correlation of entropy on coherence for a quantum state. So yeah, that's a different kind of scenario that we are not discussing today. The kind of entropy that I was talking about is on maximally mixed state, like your information is zero about the state, you have no information about the state, so entropy is maximum. But yeah, I mean, there are certain entropy calculations that you can do on the density matrix that will tell you whether the state is entangled or not. But yeah, that will, let's not go into that because we will diverge totally to a very different direction. Yeah, if there are any questions at this point, or let's do this. If there are not immediate questions, we can just do one small thing here. So we are ideally supposed to talk of noise. Why did I spend like so much time? Uh, Not exactly 1 hour, but quite close to say 40 minutes or more talking on density matrix, the block sphere representation, and everything. So let's think of noise. And for the time being, let's think that the noise is a unitary operator. And we will, just after this, we will see that that is not the main requirement. And we can have other representations like the Krauss operator representation actually comes to tackle all of those things. But for the time being, let's assume that I have noise in my system and the noise is unitary. So we also know that a unitary matrix U, it can always be represented as a linear combination of the Pauli matrices I, X, Y, and Z. So let's look into what X does, what Z does. We know what X does, right? We know that X is bit flip. It takes 0 to 1. It takes 1 to 0. Yes, we know that. But the point is that when I am talking of noise, not X as an operator, when I'm thinking of noise, it's a probabilistic scenario, right? It's exactly equivalent to this preparation example that I was talking about. The bit flip doesn't happen all the time. It happens sometimes with some probability. So when we have the state rho, it becomes with probability 1 minus p, nothing happens. So it remains rho. With probability p, an X operator operates on it. And just remember, we have seen that the operation, the unitary operator on a density matrix is U rho U dagger. It's called the super operator. So the evolution will be X rho X dagger. Of course, X dagger is equal to X. So it's 1 minus P rho plus P X rho X. what happens to the block sphere? If we want to think in terms of block sphere representation, what happens here? So again, let's draw a sphere. I wish there were some tools for drawing a better circle. This is my equatorial plane. So here we have 0. Here we have 1. Right? Now let's spend a bit of time on bit flip, and the phase flip and other things will be immediately very clear to all of us. The first thing, let's have the y-axis and the x-axis also. X-axis is something that we are more familiar with, the plus and minus state. What happens if we do bit flip on the state plus? Nothing happens. Right? So we know that plus is 1 over root 2, 0 plus 1. And if I apply an x gate on top of that, it is 1 over root 2, 1 plus 0, which is still the state plus. And if I have the state minus 1 over root 2, 0 minus 1, if I apply x here, it becomes 1 over root 2, 1 minus 0, which is minus 1 over root 2, 0 minus 1. So it is essentially minus of minus, but this is a global phase. So we can actually get rid of this. It's a global phase. So we can just ignore it. So bit flip happening on plus minus doesn't do anything. Similarly, if you see the state plus I and minus I, it is also an equal superposition. Plus I is 0 plus I1, minus I is 0 minus I1. So if you apply X gate on those, it will incur some global phase, but it won't change the state of the system. So when does it change the state of the system? If it is either 0 or 1, then it kind of flips, right? Again, we say that it doesn't really just, it is not like 0 directly goes to 1, 1 goes to 0. That is for one single operation. But a general operation is where this thing occurs probabilistically. And we all have already seen what happens if it is probabilistic. It kind of goes down slightly, right? This goes down slightly, this goes up slightly, and so on. So if I start applying this kind of bit flip operation as a noise where it's a probabilistic mixture, 0 starts going towards 1, 1 starts going towards 0, right? But we have already argued that plus and minus does not change. Nothing happens to plus and minus. Plus I minus I, nothing happens here. So what will be the scenario? If I think of in terms of the block sphere, when I apply this bit flip noise, what happens to the block sphere? It kind of, nothing happens to the equatorial part, but it kind of becomes an ellipsoid kind of thing. Because 0 is going towards 1, 1 is going towards 0. So again, this is my 0, 0. This is my 1, 1. The equatorial part is unaffected by bit flip noise. And if we keep pushing the bit flip noise more and more, and we take the probability p to half, it will just become the equatorial plane. It will just become the equatorial plane here. This is when p is equal to half. So this is the action of a bit flip error on block sphere. It changes the sphere. It kind of pushes the 0 and 1, 0 goes towards 1, 1 moves towards 0. So they kind of starts coming towards each other. The other part, the equatorial plane, remains unaffected by the bit flip noise. So we kind of get a distorted version of the block sphere where this is no longer a sphere, it starts becoming an ellipsoid. And if I can push P to half, it will just collapse, entire thing will collapse to the equatorial plane. So if we understand this, if we understand this, yeah, sorry, there are some questions I'm coming to that in a minute. Just if we understand this, let's look into phase split. We know Z acting on 0 is 0, Z acting on 1 is -1, but again, this is a global phase. This minus here is a global phase. So essentially, if we look into the Z operator, it does nothing to the state 0 and 1. But if Z acting on plus gives minus, Z acting on minus gives plus. And similarly, you can very easily check that Z acting on plus I will give minus I, and Z acting on minus I will give plus I. So what will happen to the block sphere if we think? Now, let's focus. So again, this is my sphere. This is my states 0 and 1, which now remains unaffected. I have no idea why this is happening. What is 1 minus 7? And this is my equatorial plane, which gets affected by the Z error. It's the equatorial plane which gets affected by the Z error. And so if we think that as the Z error occurs, the shrinking is along this direction. The shrinking goes along this direction, right? Uh, 0 and 1 remains unchanged. So precisely what will happen is that it again becomes an ellipsoid, but the shrinking is in this direction. It looks like this, where 0 and 1 part is unchanged, unaffected, and it's kind of the other portions which starts shrinking inside. It's like this portions which starts shrinking inside. And if I take my P to half, it will just go and collapse into the Z plane. If you say it was previous to the equatorial plane, now it will go and collapse into the Z plane. Now, if we finally think of the depolarizing noise model, which is a very important and a very easy to write down noise model. The depolarizing noise model says that with probability 1 minus p, nothing happens to the state, and with probability p, it goes down to the maximally mixed state, which is the origin. And if you break it down, you can show that it is simply p times identity by 2, the origin, because it is kind of like identity. You can break it down by saying that it is, say, 1/4 rho plus 1/4 x rho x plus 1/4 y rho y plus 1/4 z rho z. So you can break it down as an equal combination of the Pauli matrices, and it just becomes 1 minus 3p by 4 rho plus p by 4 x rho x plus p by 4 y rho y plus p by 4 z rho z. So what will happen to the block sphere now? Again, if this is my block sphere, if this is my block sphere, now if you think, what is depolarizing noise? It is all sort of Pauli's at the same time. It is all sort of Pauli's at the same time. The X will try to shrink it along this direction. The Z will try to shrink it along this direction. The Y will try to shrink it along this direction. And all the coefficients of this shrinking are same. So it kind of becomes, it still remains a sphere, but it starts becoming smaller in size. It kind of starts shrinking, and when you take p to half, when you sorry, not p to half, sorry, when you take p to 1, essentially it becomes a maximally mixed state, so it starts shrinking from all the directions. And what will happen if you just keep on shrinking, it will go down to the origin. So when p is equal to 1, it will go down to the origin. And that we have already argued before, we have already discussed this before, that the origin is identity by 2. So this is what happens. The origin is identity by 2. That's why it is kind of represented. It is also mathematically represented like this, that with probability 1 minus p, the state remains unchanged. With probability p, it goes towards the origin, identity by 2, maximally mixed state. So this is kind of the depolarizing noise model and the effect it has on the block sphere. There is something called a stochastic Pauli noise model. It's called a stochastic Pauli noise model. The stochastic Pauli noise model says that it's exactly the same thing, but the coefficients need not be the same. So it is kind of 1 minus px minus py minus pz rho plus px x rho x plus py y rho y plus pz z rho z. And px, py, pz need not be equal. If they are not equal, it's called a stochastic Pauli noise model. If they are equal, it's called a depolarizing noise model. Even here, what will happen, you can understand that this block sphere will start shrinking from all direction, but the shrinking will not be in the same rate. So in this scenario, the shrinking was in the same rate. So that's why the sphere remains a sphere, but it starts getting smaller and smaller and goes towards identity by 2. Here also it goes towards identity by 2, but in different rates in different direction. So it's very difficult to draw that because the sphere will lose the spherical structure. It will become something complicated depending on the values of px, py, and pz. And we will end up eventually going towards the maximally mixed state. But the very nice structure that the sphere starts getting smaller and smaller and then it becomes an point, that will not be here. The sphere starts shrinking in different ways. It will lose its spherical nature. It will become something very different, but eventually will go towards p equal to 1. So that's kind of, that is where perhaps we can look into what questions are here, and we can stop for a break at this point. Um, there are definitely other types of noise which I have not talked about, which we will talk about after the break. But we kind of argued that the noise we are thinking of is unitary. and we have seen all the general types of unitary noise. If it is not unitary, then it's very difficult to give a block spherical diagrammatic approach to that, because the density matrix, we kind of argued before that it still needs a unitary super operator that takes from one density matrix to another density matrix. So if it becomes a completely non-unitary kind of noise, like the amplitude damping we will see after this, then it's difficult to give such a diagrammatic approach through block sphere to this. Okay, so let's look into. Okay, yeah, thanks for this. I'll do that math results too off. Yeah, thanks for that. Let's look into the questions. Give a real life examples for pure and mixed states. It's kind of the example that I gave you. Pure state is where the state is exactly known. It is a, say, a basis state, a superposition state, everything is allowed. Mixed state comes from this classical mixture, where the uncertainty lies in the classical nature, and that mainly comes through noise. It mainly comes through noise, or it can come through entanglement. Um, but that will be kind of the examples of pure and mixed state. So there is a question, can we have mixed basis quantum states and what will be the density matrix? So, okay, I won't pretend to be an expert in this field, but yes, there is something called mutually unbiased basis and everything. Um, these were studied by Bennett and others. This will fall very much into theoretical physics or foundations of quantum physics kind of area. Um, but there you can show that you can actually create bases not with only mixed states, but with combination of pure and mixed states. The density matrix doesn't change. The basis, I mean, the density matrix doesn't depend on the basis, right? It depends on the state. It doesn't depend on the basis. You can always write it down in any basis that you want. It doesn't depend on the basis, but it is possible to write certain density matrices in a basis that contains mixed states, and these are like the mutually unbiased basis and all. Yes, so there is another question in surface and spatial, the major difference. Yes, the major difference is the mixed state and the pure state. If it is on the surface, it's a pure state. If it's on inside, it's mixed state. So this is another very interesting question, that any correlation with entanglement with this? Yes. So something that we kind of started by saying that if there is a entangled state, let's look into this state. We have a very nice representation of this state. Um, but if I ask you what are the individual qubits, there is no representation of this. So what we can do from here is, if I write it down as rho, it naturally becomes half 0, 0, 0, 0 plus half 0, 0, 0, 1 plus half 0, sorry, not 0, 0, 0, 1, sorry, 0, 0, 1, 1, 1, 1 plus half 1, 1, 0, 0 plus half 1, 1, 1, 1. This will become my density matrix. And let's just call this AB, just to say that the first qubit belongs to, say, Alice, and the second qubit belongs to Bob, the two qubits. Now, if we want to write down what is rho of A, what is the state of Alice? Because this is another question that we couldn't answer. That is given by something called a partial trace. So a partial trace can be something like, I mean, it's difficult to give a physical interpretation of what this partial trace is, but you can think of it in two ways. First, say, let's say that Alice and Bob, they shared entangled state. Bob has lost it. Now, what can Alice say about her state? Or Bob has measured it, but Bob refuses to tell his outcome to Alice. I have measured it. I will not tell you my outcome, because if I just tell you what my outcome is, you immediately know what your state is. But I will not tell you the outcome. What can you say about your state now? So this kind of questions where for some reason information coming from the other system is not accessible, that is called a partial trace, and this is given like this: trace over B. I am tracing over the B part. So I'm kind of throwing away the B part. I don't have any information out of that. That is given like, so you have the Alice part and the Bob part plus half 0, 1 Alice part trace over 0, 1 Bob part plus half 1, 0 Alice part trace over 1, 0 Bob part plus half 1, 1 trace over 1, 1 Bob part. Now, what is trace? We know trace is cyclic. So trace of AB is equal to trace of BA. This we know that trace is cyclic. So I can just use this information. So this is 0, 0, and this is trace over. Or you can do it in many ways, but or you can just say that this is trace over 0, 0 plus half 0, 1, and this is trace over say 1, 0, because I can flip 0 and A and B. That's the cyclic property of trace. 1, 0 trace of say 0, 1 plus 1, 1 trace of 1, 1. Now once more, we know this will give a inner product of 0. This will give an inner product of 0. So I am left with half 0, 0 plus half 1, 1. So what this is telling me is what I would have told you on words, that if I don't tell you after measurement, I have measured my qubit, but I don't tell you the result. What can you say about your state? Well, it has a 50% chance of being 0, 50% chance of being 1. That is precisely what this is telling us, and that is no information. And you can recognize this is again the maximally mixed state. This is the maximally mixed state that we talked of here. Half 0, 0 plus half 1. So this is the maximally mixed state. So, but it allows us to give a mathematical representation of the qubit 1, and you can easily try out the row B by doing trace over A. You will see it's the same thing, because if you measured and you refuse to tell me, it's the same problem for me. I'll say that, well, all I can tell about that state is that it's there is a 50% probability it is in 0 and the 50% probability it's in 1. So yes, this partial trace, this is called partial trace, and the maximally mixed state, this has a very big connection with entanglement. So the one last question is that we need block sphere. So there are some mathematical requirements that which I didn't cover today, because if I just go to cover that, then we haven't even touched Krauss operator yet. So there are some mathematical calculations. I would say go and see Nielsen Chuang, where you can show how a density matrix naturally corresponds to a sphere. It leads to basically 3 degrees of freedom. That gives you, and this trace of rho equal to 1. There are total 4 degrees of freedom, but trace of rho equal to 1, that's one constraint. It leaves 3 degrees of freedom. That leads to a sphere. And the mathematical representation of that it's the block sphere. It's called the block sphere, that spherical structure that we discussed. Q sphere is something that is inside Qiskit. It is not a mathematically sound mechanism of implementing something of this density matrix. But what will happen in block sphere is that if you have, say, 5 qubits, you will need 5 block spheres to represent that state. On the other hand, the Q sphere is done in such a way that it allows you to just represent everything within a single sphere. So it becomes easier for visualization, but it has no mathematical underlying structure from quantum information. The mathematical underlying mathematical formulation of quantum information is a block sphere. Okay, so I hope that answers our question, and we can take a short break right now.
Sure, sir. We can take about 5 minutes break if you want.
Okay, yeah, let's take a 5 minutes break and maybe we come back at 4:25 or something.
Okay, sir. Sure.
Okay, thank you.
Welcome, sir.
Hello.
Yes, sir.
Yeah, sure.
Hello.
Yeah, hello. Am I audible now?
Yes, sir, you're audible.
Okay, good. Should we start?
Sure, sir. We can continue.
Okay. Okay, great. So,
Sir, your screen sharing is went off.
yeah. I'll share the screen. Is this visible?
Yes, sir, it's visible.
Okay. Okay. So, yeah, welcome back to this this very short 5 minutes break. Um, so there are four topics that are mentioned here. I won't go into all of those, as I said even in the beginning that unfortunately the topics I get are very mathematical. So we will do some part, at least not the entire thing. At least we will skip some, but we will do some of these portions. One of the questions that was there before we stopped was to give a real world example of pure state and mixed state. So there is one theorem, I have forgotten by whom, but that theorem kind of says that there is nothing called mixed state in the universe. It's because, so you saw how we got a mixed state by taking a partial trace from an entangled state. So the idea is that a system, if it seems to be in a mixed state for you, it is actually entangled to a much bigger system. And just because you are unaware of the entire system and the environment together, you don't know. It's because of your ignorance. It's because you are looking into only some part which you are calling the system and not the entire environment. That's why it appears as a mixed state to you, but ideally everything is pure state. So that is kind of the representation that the Stein-Spring representation is going to take. The first is that we kind of said that every operation that we looked into till now, just be it evolution, be it noise, everything was unitary. And when everything was unitary, there are certain limitations of that. For example, it is not possible to add a system. When you do error correction, say k qubits are encoded into n qubits. So from k, it enlarges to an n qubit system. If you preserve your representation to unitary, then you cannot increase the dimension of the system. A unitary operator always preserves the dimension. So you cannot do something like this encoding that a system gets enlarged. It adds new system. Or even the partial trace that we talked about, you discard some part of the system. We talked about partial trace involving entanglement. But think of this, that when we do again error correction, perhaps some of you have seen in some other QTs. If not, you will. Um, so even in error correction, we first encode the system. So that means we are taking, say we take the Stein code 1 to 7. So 1 qubit gets encoded into 7 qubits. So that means the size of the system gets increased. Now there is noise in the middle. Then we kind of add some ancilla qubits. So now the size of the system even enlarges. We measure the ancilla qubits and we discard them. Depending on the outcome of the ancilla qubit, we make some corrections on the actual state and we discard the ancilla qubit. So that's kind of a partial trace that we are doing here. Again, it's the same thing because the ancilla states, when we kind of do the syndrome measurement, it gets entangled with the system. But anyway, that is more of a physical example. So this slide contains, I'll send all the slides and everything to you. This slide contains what we have already seen mathematically, how to get a maximally mixed state out of this. This is something that we already discussed, that When we think of vectors, these are kind of given by LA and LB. These are linear operators acting on A and B. They can be unitary. So if we look into, if we say that this L act from A comma B, it means it's a linear operator that takes a vector A to vector B. This is okay for a state vector notation. But when we have a density matrix notation, these matrices themselves are the representation itself is a operator. So we need an operator L which acts on operators which take one operator to another operator, and it's called a super operator. Similarly, partial trace can also be a super operator, that you have a bigger density matrix and there is an operator which maps a bigger density matrix to a smaller density matrix. You throw away the B part. It takes a bigger density matrix to a smaller density matrix. So it's an operator. It can also be a super operator. So when we think of quantum operation, it can be unitary, it can be adding systems, it can be partial trace. All of them come together. And here we have this idea of something called an isometry. So it's kind of going beyond what unitary allows us. Unitary doesn't allow us to increase the size of the system. So isometry is something that we will define. It goes from a vector space with dimension dA to another vector space with dimension dB, where in general dB can be greater than dA or can be equal. We are not thinking of dB is less than dA at this point. Partial trace we will treat as a separate thing, because we kind of said that unitaries plus adding systems plus partial trace, these two taken together will be isometry and partial trace will remain separate. So when you can understand when dB is equal to dA, this becomes unitary, but dB can be in general greater than dA also. And here the requirement is V dagger V should be equal to identity, and the identity should act on dA. But anyway, V dagger V should be identity. There is no immediate requirement that V dagger should also be identity. If V dagger is identity, it can happen only if this is a unitary. So isometry is something a bit bigger, more than unitary. It contains unitary at the same time, but it can be something beyond unitary as well. So what it does here is, this is some, if you look into the norm of this and if you do some simple calculation, you will see that isometry also preserves the norm. Although it's not kind of unitary, it still preserves the norm. And therefore the name isometry comes from iso plus metric, that it's the same length metrics. So once isometry is here, what we have is we can now add systems. Great. So the other thing that we want to look at is, just give me a second, something went wrong here. Let me share once more. Okay. So now, as we said that what is a quantum system? What is a quantum operator? It's unitary plus adding system. They are taken together as isometry along with partial trace. Now, what is said here is, if you have a sequence of isometries, partial trace, and everything, you can represent everything together as a single isometry followed by a single partial trace. So the question is that how is that possible? So let's say that we have a set of operations on some isometries. They can be unitaries as well, but we will look into the more broader scenario and call them isometries. It's an n qubit system. So the first isometry is acting on n qubits. Remember, it can act as identity on some part. So for example, if it's just an unitary and say it's an X gate acting on qubit 1, whereas it's a 5 qubit system, we can always say that it's X acting on qubit 1 and identity acting on 2, 3, 4 or 5. So this entire thing, X tensor identity on the rest, this can be treated as a unitary or as an isometry. So say we have the first isometry, second isometry, then we trace out qubit I, and we are left with n minus 1 qubits. Now we act another isometry, we trace out qubit j, qubit k, two more qubits are gone. We are left with n minus 3 isometries, and so I'm sorry, qubits, and this isometry acts on n minus 3 qubits. The first thing, and this first step is actually the sufficient if we understand this. Can I interchange the order of these two? Yes, because if I take V3 here, what is happening? It is acting on n minus 1 qubits, right? Let's say that I have a 10 qubit system and I have traced out the last qubit just for the sake of convenience. So now my isometry acts on 9 qubits. I can say I can always expand that isometry such that it is acting on 9 qubits and it is acting as an identity on the 10th qubit. So the isometry changes slightly, but we can write it like this, that it's some v prime 3 that now acts on n qubits. On ith qubit, it acts as identity. So the moment we can do that, now we can actually take all the isometries together, like we can start moving this and we can take all the isometries together. We can combine them as a single isometry Vn, and we can take all the partial trace and we can combine them as a single partial trace that will trace over I, j, and k together. Instead of saying that individually, I will first trace out I, then trace out j, then trace out k, I can just say that trace out ijk. So any quantum circuit can be represented as a single isometry followed by a single partial trace. Now, the first problem of this time spring representation that I say, that when you have a mixed state, the thing that the time spring representation will say is you have a mixed state because you don't understand it, because you don't have the representation of the entire environment. You are only looking into the system S that is of your interest, but the system is entangled with the environment E. If you look into the entire system environment together, then there is nothing called a mixed state. Everything is pure. What is the problem of this? So everything is pure, that means it's always a unitary operation and everything, things become very simple mathematically. But what is the problem of this? There are two problems. First is, I am always not interested in the combined dynamics. We are not always, I have a qubit. I want to know how that qubit is um, evolving. I don't want to know what happens to the entire, all the molecules in my room. I am not interested in that. So I don't want to know this combined dynamics. And the second thing is, it is also not always possible to know the combined dynamics. How do we know I have a qubit, what is the environment that it is interacting with? It will be a huge representation. And at the same time, we may not have the proper information, the total information of the entire environment. I know what I am doing to my qubit. I know what sort of Hamiltonian I am applying, how I am evolving the qubit, but what it is doing to the entire environment, I may not know and I may not care. So this idea of doing this time spring representation, where everything you represented as the system and the environment and evolve it unitarily, that may not hold always. So the idea here is that, so let's say that the first part is the system and the second part is the environment, and it's in a density matrix notation. So now what we can say is, if I look into an operator acting on this system and the environment together, then I can choose a basis for my environment, right? It may not be a single qubit basis. It can be 100 qubit basis. That's a different issue, but I can always choose a basis for that. So now I can say that, okay, this VE belongs to my system and this E belongs to my environment. If there is any coefficient other than E, I can actually absorb it within VE. V can be a matrix. V itself can be a matrix. So now what I need is, just by isometry, I know that V dagger V should be identity. This is something I know. This is the requirement of isometry. V dagger V, the entire system and environment taken together. But if you just put in this same thing here, what happens? V dagger is V dagger tensor bra of E. I'm just calling it some E1, and V will be sum over some E2, VE tensor E2. Now let's separate the system and the environment out. We have VE1 dagger VE2 tensor E1 E2. Now remember, E is a basis, so it's an orthonormal basis. So when E1 is not equal to E2, this inner product is 0. When E1 is equal to E2, this inner product is 1. So it's a Dirac delta function, and this Dirac delta function only exists when E1 is equal to E2. Call it E. So I end up having a scenario where we have this sum over E, VE dagger VE. Tensor, this is just 1. So there is not much tensor here, right? Um, so this, but what it means, this portion is acting on the system. So I have been somehow able to trace out, in some sense, I haven't traced it out, but in some sense, I have been able to say that I will ignore my environment completely, and I can do that by this representation. Now my system evolves as this sum over VE dagger VE, and this VE, these are called the Krauss operators. Each of these VE is called a Krauss operator. Note that previously the requirement for isometry was V dagger V should be equal to identity. Here the requirement is sum over all Krauss operators, this VE dagger VE should be identity. Each of these individual terms may not be identity. So for a particular E, VE dagger VE may not be identity, but when you sum over all E, it will definitely be an identity. So this is the requirement of Krauss operators, and any channel, any quantum channel that you have, you can represent that as Krauss operators by and followed by a partial trace, where you can understand what we did here was kind of trace out the environment. That's what we said, that we will trace out the environment, and that gives me we previously argued that any quantum dynamics is a single isometry followed by a single partial trace. And this is what we are seeing here. The partial trace I will take over the environment. The isometry is over the system and the environment. But by using this trick, I can actually trace out the environment and get back only the system. And the system evolves like this: VE row, VE dagger. Even if, see, note one thing, we will show this before. Even if this is unitary, it is not always guaranteed that each of this term is unitary. In general, there is no guarantee here. So each of this evolution is an evolution. It may not be an unitary evolution, but the fact that it preserves the norm is maintained through summation in Krauss operators. So this is how that what we argued, that any quantum dynamics is a isometry followed by a partial trace. That gets converted to saying that any quantum dynamics can be represented as Krauss operators. So these VE are my Krauss operators. Let's look into some examples. If I have a very simple unitary evolution, that's the simple possible thing that we know, that the system rho evolves as U rho U dagger, then U itself is the Krauss operator. Very, very simple. And for this case, there is only one U. So U dagger U is equal to identity. There is no summation. There is no summation, only a single Krauss operator. So that one also follows. Say I have a Krauss operator that comes from a probability distribution. If you can identify something like this is a depolarizing channel, where we said that with or a stochastic Pauli channel, that with certain probability we have X gate, Y gate, Z gate noise operating, and with some probability we have nothing happening. That means identity is operating. So you can say that UE is, say, all the E's, these U are identity X, Y, and Z. So each of the probability, square root of that times UE is the Krauss operator. Why square root? Because you need to apply it on both sides. So when you apply root PEU, root PEU dagger, the two root PE becomes PE. So that's why we have this type of unitary operator, like the depolarizing noise model, stochastic Pauli noise model. They can also be represented like Krauss operators. Even partial trace can be represented as Krauss operators, but yeah, that's kind of the Krauss operator will look something like this. Let's not go into this detail. We need to go to a few more things. So this is kind of a very interesting channel. We say that a quantum system, when we prepare a qubit is always prepared in the state zero. How do you do that mathematically? Because you take a qubit, the qubit may not be the state zero. How do you do that physically? Well, you keep it for certain time and you can expect that it has kind of released extra energy. We will look into that very soon. It will release extra energy and it will kind of damp down to the state zero. This is what we expect physically. But what does it mean when I say mathematically? How do I represent that? I take a qubit and I map it to zero. It is represented by these Krauss operators. If the qubit is in the state zero, it does nothing to it. If the qubit is in the state one, it maps it to zero. You can immediately see that this is not a unitary operation because zero gets mapped to zero, one also gets mapped to zero. The reversibility criteria is not maintained. So you cannot have a unitary operator that will kind of show how do you prepare a state in zero. You need a Krauss operator representation for this. I mean, this is kind of an example where, I mean, you could have said here that, okay, measurement is there, unitaries are there, what extra is Krauss operator doing? Here is one example where unitaries fail and you need Krauss operators. We have already talked of depolarizing noise model. This was a depolarizing noise model, and it is exactly this noise model. And you can have the Krauss operators like this. Let's look into this amplitude damping channel. This is what we were just talking of, that if I prepare a system in the state zero, it is the ground state, nothing happens to the system. If I prepare the system in state one, it has a tendency to release the extra energy and go down to the state zero. So how do I represent this? See, this is again not unitary because zero remains zero, one goes towards zero. This is not reversible. Um, this does not satisfy the criteria for reversibility because zero is also going to zero, one is also going to zero. So if you look into the output, you cannot uniquely tell what is input. So the first thing is, if the system is in zero, this is my environment. If the system is in zero, it remains zero. If the system is in one, with certain probability, nothing happens, but with some probability, it releases this extra energy. The environment gets excited. It goes to the state one, but the system goes down to the state zero. The Krauss operator corresponding to this is like this. I mean, these are very well-defined Krauss operators. So the Krauss operator looks like this. And if we look into the action, let's say that I have a state like this. This is the plus state, 1 over root 2, 0 plus 1. And you can just check that the corresponding density matrix will look like this. If you apply this V0 row V0 dagger on it, this is what it does. V1 row V1 dagger on it, this is what it does. And when you add, so this is how the system evolves, right? Sum over VE row VE dagger. This is how the entire system evolves. Let's look into two things first. Let's not worry about the diagonal terms. We already discussed this, but this is a real example of this happening. Let's look into the off-diagonal terms. As P tends to 0, the off-diagonal terms goes away to 0. So this is what we said is decoherence. The system loses its coherence. The system, when we said this is a superposition state, this is a pure quantum, like this is not classical. Superposition has no classical correspondence. This is pure quantum. And yet, as we apply the amplitude damping channel on this, and we see that as p tends to 1, this off diagonal terms goes off to 1, so goes off to 0. So it loses the coherence and this becomes a classical distribution. You can say that, okay, but here I see that this term is also going towards 0 when p goes to 1. Yes, because what is happening here? What is happening in amplitude damping? It has a tendency to go down towards 0, right? It is as p tends to 1, the system settles down in the state 0. And what is the representation of 0? Matrix representation 1 0 0 0. So that is what happening, that as you take p to 1, this will become 1 0 0 0, and the half here, this will become 1 plus 1, so 2, the half will kind of take care of that. So this is going towards the state 1 as p tends to 1. And you can actually check that as you measure, if you measure the system, then at some point the probability of getting the outcome 0 is 1 plus p by 2, and the probability of getting the outcome 1 is 1 minus p by 2. So as p increases, this probability of outcome 1 is decreasing, as and the probability of getting 0 is increasing. And at the same time, the off diagonal terms goes off and it vanishes to 0. So it loses its quantumness, it becomes a classical state. On top of this, so we discussed Krauss operators, and we kind of said that any quantum channel can be represented as a Krauss operator. We kind of talked of all those unitary operators, even state preparation, amplitude damping, the non-unitary ones. So we see that it can represent both unitary and non-unitary. What we didn't walk through properly, but I kind of just mentioned, is that you can even do a Krauss operator representation for measurement, for partial trace. So Krauss operator takes care of everything. So why we need a CPTP map? So the reason for this is, let's look into a quantum channel. What should be the properties of a density operator? First, it's Hermitian. So it kind of means that the eigenvalues are real. Once more, eigenvalues are real because they are probabilities. They cannot be complex. We have seen that the trace of rho should be equal to 1 because the sum of all probabilities is equal to 1. And rho is positive semi-definite. That means all eigenvalues should be greater than equal to 0. Once more, the eigenvalues correspond to the probability. Now, any map that preserves all three of these is a valid quantum channel, and Krauss operator preserves all three of these. But the question is that let's say that I have a 2-qubit system. I have a 2-qubit system like this, and I want to take transpose, right? I want to take transpose of the system. If I transpose the system, so you see I and K, they are interchanged here. J and L, they are interchanged here. This is the transpose of the system. And it satisfies that if rho is greater than equal to 0, then rho transpose is also greater than equal to 0, which means that if this is a valid density matrix, this transpose is also a valid density matrix. And you can just check with one example of a Bell state here, that the eigenvalues of the rho and its transpose are all like non-negative. So it's fine. So that means that what we just showed here, what it means is that you can take transpose as a valid quantum operation. It should be a valid quantum operation. But let's take something called a partial transpose. So what we did in partial trace, we trace out some part of the system. Similarly, what we will do in partial transpose is, say I will transpose only the second qubit, only B. I'll transpose only second qubit. So you see I and K remains as it is, J and L are interchanged. And similarly, if you transpose A, then K and I and K, they are interchanged, J and L remains the same. Now let's take an example. I have this 2-qubit system, and previously this is the entangled state that we saw. It was the entangled state. Previously we saw that when I take the state and I transpose the entire state, it still remains positive semi-definite. But here, if you transpose only on B, so see 0 and 1 gets interchanged, 1 and 0 gets interchanged. Now, if you take the eigenvalues of this partial transpose, there are negative values. So that means this is no longer a valid quantum state, because now my eigenvalues don't correspond to probabilities. This is no longer a valid quantum state. And let's not go into that. There is something called a Perez-Horodecky criteria. You can kind of understand that this is not really a entangled state, because we end up having 0, 0, 0, 1, 1, 0, 1, 1, all of them. Actually, we had only 0, 0 and 1, 1. Now we have all of them in some sense. There is a criteria that if the joint density matrix is separable, then its partial transpose is positive. But anyway, so the observation here is that transpose, when acting on the entire system, it takes a positive system to another positive system. But if the transpose acts on one part of the system, it takes a positive system to a negative system. It can take a positive system to a negative system. So this cannot be the property of a quantum channel. A quantum channel or a quantum map, it should keep both the composite system. So if I take the entire system, say I have an n qubit system, if I evolve the entire n qubits, it should take a positive system to another positive system. If I apply some operations on only say k out of n, it should still take a positive system to another positive system. So this is something called positive, going from positive to completely positive. That means it is not only positive when you evolve the entire system, it is positive when you evolve any subset of that system. It should remain positive. If that happens, then it's called a completely positive system. And therefore, we say that a valid quantum channel is something a bit more than Krauss operators. Krauss operator, again, is a valid quantum channel with, when you say that, okay, I have defined a channel, I can give a Krauss operator representation to that and everything. That doesn't make it a valid quantum channel. What makes it a valid quantum channel is that it is completely positive trace preserving. The trace should be preserved. That means like the sum of all the diagonal is 1, which means the probability of getting an outcome sums up to 1. But it should also be completely positive. That means when you evolve only one part of it, if you evolve the entire system or any subset of the system, it should still take a positive system to another positive system. Only when your operation, whatever operation you define, satisfies this requirement, then you give a Krauss operator representation to that, it is a valid quantum channel. But just saying that I have a Krauss operator representation is not sufficient. You need to show that it's a completely positive state preserving map. So this CPTP is the full definition that you want to have for a valid quantum channel. I won't go into this. There is something called that how do you take a CPTP map to a Krauss operator, that is done by something called Choi operator. Let's not go into this. This is a bit mathematically involved. But anyway, as I said, that if you have a CPTP map, you can always have a Krauss operator representation of that. But just because you have come up with a Krauss operator representation may not imply that the map is completely positive trace preserving. If it is not CPTP, it's not a valid quantum channel. If it is CPTP, there is a Krauss operator representation to that. So any valid quantum channel, you can always represent that with a Krauss operator. And I'll share this things with you. If you are interested, just go through this portion, how you can construct the Krauss operator by something called this Choi matrix and all. So maybe we should stop here. And if there are questions, we can take those. Also, what you can do here is, I mean, all of these things that I kind of discussed are, if you just go to my GitHub, the handle is my name followed by a one. There is a repository called teaching, and in this, you will see all the different notebooks. These are, I mean, some of the notebooks I used for other FTPs in other QTs before this, but that's not important here. Um, but you can go to this handwritten notes if you want, and what we were discussing about Blocksphere, these are all here, whatever we discussed today. Yeah, I'll share the GitHub link here. And if you, the intro to quantum channel that I was just showing the PDF, it's also available here. And if you want to see how to build different noise models, you can just go to this notebook. It is also available if you just search on Qiskit, but you can also check here that how you can build all these different noise models that we talked of, like bit flip channel, phase flip channel, different how yeah. So different how it affects the outcomes. How do you do that using Qiskit? And how do you do a depolarizing noise? What happens in depolarizing noise? Like I would definitely say go and run this notebook, because here, as you can see, that we were looking into an circuit. I was looking into a circuit whose ideal outcome should be either 0, 1 or 1, 1. And as I keep increasing the probability of error in depolarizing noise, you see all the outcomes are actually, this one is decreasing, this one is decreasing, this is increasing, this is increasing. They are coming towards equal distribution. That's what we saw, right? It goes to the origin, so it becomes a maximally mixed state. How do you create Krauss operators using Qiskit.quantuminfo? How do you take a noise model and create a Krauss representation of that? How do you actually take a Krauss representation, create a Krauss operator? This is the state preparation um, Krauss that we were showing, that you take anything and you map it down to zero, and you can see it is not unitary, but it's definitely CPTP. That's all. How you look into different measurement errors, thermal relaxation that we talked about, and just showing here that, so when we have, this is the original scenario, when I have taken the thermal relaxation parameters from the current IBM Pittsburgh. This is the one of the latest devices that we have. And you see that the devices are so good at this point that for the small circuit that I have taken, it is not really affecting too much. But if I reduce the T1, T2 values, like if I increase the relaxation parameter, that is the green portion, you see that it is actually kind of putting everything down and speeding towards all zero and everything. So, and how do you take a complete noise model from one of the backends, and you can run that, and you see, as I just said, that at this point this is a very small circuit and the backends are pretty good at this point. So hardly anything happens here. But yeah, I'll just share everything. Maybe the link is not correct. This should not be just yeah, use this one.
Afternoon, sir.
Yeah.
Um, so we have anything else?
No, I think that's all from my end. If there are no more questions,
So participants, if you have any question, kindly type in the chat box as quickly as possible. We are almost towards the end of this session. I think, sir, there are no questions. Uh, let us conclude then. It's 5:07. Thank you very much, sir, for the informative session. As from the interaction of the participants, we can understand the participants really like the session and they're really involved in the session, to be precise. So thank you, sir. Thank you for your time. Sir, I have a few requests to you.
yeah,
Uh, First of all, sir, will you be kind enough to share the PPT and the notebook that you're writing in?
yeah,
Kindly
yeah,
share
yeah.
so
Sure.
that we upload that in the canvas. Also, sir, if you can share 4 to 5 questions.
Okay, okay.
Right,
Yeah,
sir.
sure.
The academy will get back to you, but kindly share on that. So we'll add that on the quiz too that we are going to have next week.
Okay, sure, sure. I'll share.
Thank you, sir, for such informative session. We have been here also listening to you, and thank you very much for this informative session. There are many doubts that we are having previously also. Those are cleared up to us also. Thank you very much, sir, for your time.
Thanks a lot.
So, participants, that's all for today. I think this is the end of day 10. Next, we have Monday, another session, continuation with this. So, see you on Monday, 3 p.m. sharp. Kindly join within time. I think we have enough time to celebrate the Dasera and kindly be on time from Monday. So, thank you, everyone. Thank you, sir, once again. And bye bye. We'll see you on Monday. Thanks.